Welcome to Recitation for Chapter 9. The problems you're responsible for this chapter to upload are problems 9-3, 9-4, 9-5, and 9-8. We will be talking about covalent bonds. You definitely need to learn how to write Lewis structures, and we'll talk about bond enthalpy. Okay, so this is problem 9.1, 9-1. Identify all the different types of bonding, ionic, covalent, or both, in the following compounds. Hopefully you're already doing this since you had to do this in order to name the compounds back on the first exam. You can look at example 9-3 on page 398 in your TRO textbook. That might be helpful. And what you're doing here is you see sodium chloride. Well, you look at your periodic table. 2/3 of the elements on the periodic table are metals. They're either alkali or alkaline earth metals or transition metals. So sodium is a metal and chlorine is a nonmetal. And so if you remember, when you have a metal with a nonmetal, they form charges. You have a cation and an anion. So you have a sodium plus and a chloride minus. This forms an ionic bond. So in this case, it would be an ionic bond. Okay, the CLO2, you have chlorine with oxygen. Both of these are nonmetals on your periodic table. So a nonmetal with a nonmetal, that is going to be a covalent bond. So these will be covalent bonds. And that means they're sharing of electrons. There's no plus and there's no minus. Naming these would be chlorine dioxide. And then here we have a metal, barium, with a polyatomic ion. Okay, so these are nonmetals. And then we have in our polyatomic ions with chlorine with oxygen, this is going to be a nonmetal with a nonmetal. And so you also have the metal barium, which is a 2+ charge, and then you have perchlorate, which is a 1- charge. This would be both. You're going to have both kinds of bonding here. So the answer to that is both. The next problem is 9-2. And this topic is bond polarity. You don't have to know. Page 397 for the exam. Okay, so describe the charge distribution in this molecule. The first thing you want to do is you want to draw your Lewis structure. So when you're drawing the Lewis structure, the first thing you do is you write the skeletal structure. Now, the steps to do this is in section 9-7 of your book. And so the first thing you're going to do is draw the skeletal structure, and hydrogen will never be your central atom, and you want to put the most electropositive element in the center. So in this case, you're going to have sulfur bonded to hydrogen. Hydrogen will always be a terminal. Okay, the second thing you're going to do is you're going to calculate your total valence electrons for the whole molecule. So hydrogen has 1 valence electron, and there's 2 of them, 2 hydrogens in this molecule. And sulfur, it's the same group number. Okay, so hydrogen's in group 1, so it has 1 valence electron. Sulfur is in group 6, it has 6 valence electrons. There's only 1. So the total here is 8 valence electrons. So then when you put these in, you want to, when you have a bond, okay, valent bond, that's going to be 2 plus the other 2, so that's 4. You want to, third thing you do, you distribute the electrons around the atom. Now keep in mind, so we're going to distribute the electrons. Hydrogen forms what we call a duet, means 2 electrons satisfies its outer shell. If you remember the electron configurations, because then it has an isoelectronic configuration with helium. And everything else forms an octet, except for the exceptions to the octet, and that's in your last section of this chapter. So hydrogen here is going to get to, we distribute the electrons first to your terminal atoms or elements, and then you work to the center and you satisfy the duet or the octet. So we've already satisfied hydrogen. Hydrogen has 0 lone pairs. They're always going to be in the bonding. So that's 1, 2, 3, 4, 5, 6. Remember, we have 8 here. It's 1, 2, so 5, 6, 7, 8. And then we check to see if all the octets are made. So this is fine, and sulfur has 1, 2, 3, 4, 5, 6, 7, 8. So that's a correct structure. Now, this particular compound or exercise is asking about bond polarity. And so this is within the hydrogen-sulfur bond. So we're talking about within here. Now, your electronegativity, you have, this is section 9.5 and 9.6, page 394 and 395. So you need to read those pages. The electronegativity. Basically, it increases electronegativity up a group and across a row. So fluorine is the furthest. Electronegativity is how attracted these elements are to obtaining an electron. It's how much it will pull the electron. It's almost like a tug of war between this bond. And fluorine is the most electronegative element with a 4.0. It's up there in the upper right hand corner. The noble gases are inert, so we don't really focus on those. And then francium is at the very bottom, and it's 0.9. So it doesn't really want an electron. Well, remember the alkali earth metals, or the alkali metals as well, they want to give up an electron. So they really don't want to attract electrons. But you get up here in the halogens, like where the fluorine is, and you have more electronegativity. So sulfur is over here on the periodic table, and hydrogen is over here. So what happens is the hydrogen within this bond is delta positive, and the sulfur is delta negative. And you do these little delta negative, and the hydrogen is delta positive. Another way to show this is to do like a plus, and you can do this for each bond. And then you have the overall polarity for the molecule, which would be written such as the lone pairs are definitely going to be negative, and your overall molecule goes like this, where the electron density is around the sulfur. All right, so 9-3. This is bond strength. This is section 9.10, and this section talks about bond energies and bond strength. And I always hear Dr. Meyer say, short and strong. Okay, so your short bonds are stronger bonds. So if you look at table 9.4, you'll see the length of these bonds for HF is 92 picomolar. HI is 127 pm, and then HI is 161 pm. So remember, short and strong. So which one's your strongest one? And the length here. So HF is shorter, and then you would have HCl, and then you would have HI, hydrofluoric acid. Hydroionic acid, iodic acid. Now, think about this. These guys, hydrogen. Now, hydrogen is a 1s orbital. You all learned that from last time. It's a small size orbital. And the strength of bonds and the length of bonds are how much overlap you have. Fluorine has these p orbitals, right? The valence electrons, and they're going to overlap here. And what's nice about this bond, you're going to get more overlap with these orbitals because they're similar in shape. Okay, fluorine is on n equals 2, and hydrogen is n equals 1 energy shell. And that kind of gives you an idea as well of is the size of those orbitals. Let me get a periodic table here. So you look at HCl and Cl now. For Cl, it's in what energy shell? It's in 3. So you get bigger orbitals. And chlorine has a bigger orbital that's different in size from hydrogen, so you're going to have less overlap. And that's what makes the bond longer. And same thing with the iodide. Iodide is in n equals 5. So you have even less orbital with this hydrogen here. And it shows in the 161. Okay, now we're dealing with the same elements, nitrogen and oxygen. They're bonded to one another, but you're dealing with a single bond, a double bond, and a triple bond. And if you look at the tables, so these bond lengths I'm getting, these are in table 9.4, you'll see that this one's not listed, the triple bond, but the single bond is 136 pm and the double bond is 120 pm. So what do you think? If you were to rank these, we'll go the short ones. In triple bond oxygen is going to be shorter than in double bond oxygen, which will be shorter than in single bond. And short and strong, so these bonds are going to be harder to break. So they're going to be pulled together more, and therefore they're going to be shorter. Next problem is problem 9-4, and it says use the molar bond enthalpy data in the table to estimate the value of the delta H of reaction for this equation. Now, when you're calculating, I'm going to come down here for a second. Okay, when you're calculating these, there's some rules. So this is section 9-10. It's page 409. And if you look for another example, example 9-11 on page 412. And in this, you'll see that you first rewrite the reactions using appropriate Lewis structures and molecules involved. Well, the nice thing is this problem already gives it to you. You have to determine which bonds are broken and which bonds have formed. So we're going to determine bonds broken, and we're going to determine bonds formed. And then we're going to sum up these. So you're going to use this equation. And so we're going to have the delta H of the reaction equals the sum, that's the summation, of the delta H of all your bonds broken. And we're going to keep this a positive value. This will be a positive. And then we are going to add the summation of your delta H of your bonds broken. And since bonds, when they break, this produces a negative enthalpy, so that will be the negative. So we'll sum up all the negative energies of these bond energies. So here's the bond energies. They'll always be given to you in a table. You'll never have to memorize them. But you'll take the positive value for bonds broken, and then you'll take the negative value for bonds, for bonds formed. Bonds formed will be the negative. Bonds broken will be the positive. It always takes energy to break the bonds. When bonds form, they give off energy, so that would be negative. Okay. And so, doing this problem then, if you look at here, we have 3 NH bonds. These are broken. You can look on the reaction side. And we have 2 oxygen double bonds broken. And then for bonds formed, we have 2 N single bond O's formed. We have 1 N double bond oxygen formed. We have 1 OH bond formed, and we have 2 OH bonds formed here. Okay. So then we come down here and we're going to total them up. So actually I'm going to go ahead and for the bonds broken, I'm going to circle them in red. So we see if we find NH, do we see NH? Here we go. That's going to be a positive 390, and we're going to take this times 3. And then we have an OO, oxygen 502, and we're going to take that times 2. And then for bonds formed over here on the product side, we're going to see the NO, and I'll put these in a box here. So we're going to have 2 of those. You see that bond there? That bond there is the NO. And then we have the N double bond to the oxygen. That was a bond formed. And then we have this OH bond formed, this OH bond formed, and this OH bond formed. So we're going to use this, and we're going to use that 3 times. And we're going to now sum them up. So we will, the delta H of reaction will equal, we'll do bonds broken in red. So remember we had 2 times 502, because we have 2 oxygens, plus 3 times the NH, 390. And then we're going to add this. And remember, this is going to be the negatives. So plus, and we had, let's go back up here and look, make sure. So we had 2 oxygen double bonds, 3 NHs. And then over here we have 2 NOs. 2 NOs. So we can just put the negative there if we want. We'll Oh, not what I want to do. Okay, so let's just do it this way. 2 times a negative, and do we say NO201 plus, that's the NO, we had 2 NOs. We have 1 N double bond O, so that's plus one of these, which is negative 607 right there. And then how many? We actually had 3 OHs. So there's our OH here, 464. So we had plus 3 times negative 464. And when we solve this, then get my calculator real quick. Okay, now we're going to writing Lewis structures, problem 9-5. Okay, so the central position is going to be the less electronegative atom or element. Okay, so when you look at this, you have hydrogen, which is going to be a terminal. And a lot of times when they're written like this, they're kind of telling you the order. And then carbon is going to be your central. And if you look at page 395, you have electronegativities. You don't have to memorize this. You do have to know that your increasing electronegativities is up a row and across a row. So increasing electronegativity is up a row, up a group, and across a row. And you have hydrogen over here. You have carbon, and you have chlorine here. So carbon, if you look at page 395, you can see the actual electronegativity is 2.5, hydrogen is 2.1, and chlorine is 3.0. So carbon is the central position, chlorine is going to be connected to the carbon, and there are 3, because you see the 3 subscript. Okay, the second thing you need to do is total valence electrons. I just write that as VE. So hydrogen has 1, and there's 1 because it's in group 1. Carbon has 4, and carbon is in group 4 because you don't count the transition metals. And then you have chlorine, and there's 3 of them, and chlorine is in group 7. So that's 21. When you total 21 plus 4 plus 1, you have 26 valence electrons. So the third thing you need to do is you want to distribute the valence electrons. And so you have 2 in each covalent bond, and then you place the rest on the terminal positions, terminal atoms. And you want, in hydrogen, you want to give it a duet. The other ones, you want to give them an octet. And then you go from there. So let's count electrons. We have 1, 2, 3, 4, 5, 6, 7, 8. Hydrogen's already done. So 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26. And that's 26 valence electrons. Now you check, the fourth thing you do is check to make sure each has its complete octet. So hydrogen has 2. Chlorine has 1, 2, 3, 4, 5, 6, 7, 8. This one has 8. This one has 8. And then carbon has 1, 2, 3, 4, 5, 6, 7, 8. So every atom has its complete octet, and you can draw these as such if you want to redraw it to make it neater. Hydrogen and chlorine. And some people draw them like this. I like to actually draw my electrons in, but that is also correct. And that is, well, in that case, you show all unshared pairs of electrons and the formal charges. Okay, so formal charge. How do you do formal charge? Well, your formal charge formula you have to do for each atom equals the number of valence electrons minus the number of non-bonding electrons plus 1/2 of the number of bonding electrons. So let's do hydrogen. Formal charge for hydrogen. Hydrogen has 1 valence electron minus 0 non-bonding electrons plus, so 1/2 of the bonding electrons, you have 1, 2. So 2 divided by 2. So the formal charge would be 0, because 1 minus 1. Formal charge for carbon would be its total valence electrons is 4 minus, has no non-bonding electrons, plus it has how many bonding electrons? 1, 2, 3, 4, 5, 6, 7, 8. So 8 divided by 2, and this works out to be 4, so 4 minus 4 is 0. And then the formal charge for chlorine, since chlorine's all bonded equally the same here, in this particular molecule, we can just do this one time. Chlorine's valence electron is 7 minus, each one of these, you just pick one, just do this one here. You have 1, 2, 3, 4, 5, 6. you have 6 non-bonding electrons. And then we're going to add half of the bonding electrons, which would be 2 divided by 2. So that would work out to be 1. 7 minus 7 is 0. So each one of these elements have a formal charge of 0 in this molecule. This problem is 9-6, and let's make a correction here. This should be NH4 plus, okay? So include the ammonium is got a plus charge. So we're going to draw this skeletal structure. You're going to follow section 9-7, examples 9-4, 9-5, and 9-6. We also are going to look at the formal charge, because we're going to do formal charge. That's on page 403. 403. Page 403. And here, your central atom is going to be nitrogen, because hydrogen is always on a terminal position. So you go ahead and draw that in. The second thing you do is your total valence electrons. So each hydrogen, there's 4 of them, and they each have 1. And the nitrogen is in group 5, so it has 5 valence electrons. Now your overall charge, and you put this in a big bracket, and you put a plus there. And then so when you have a cation, you're going to take away a total valence electron. Okay, so for the plus charge, you want to subtract 1 electron. So what is this going to be? This is 4 plus 9. 4 plus 5 is 9 minus 1. You're going to have a total of 8 valence electrons. Okay? So now you add them in. You'll have 1, 2, 3, 4, 5, 6, 7, 8. And that is the Lewis structure. Pages 390. I just wanted to give you the pages here. 398 through 400. Now to do formal charge, you're going to do a formal charge for the hydrogen. So here we have the formula, which is total valence electrons minus the number of non-bonding, we'll just put NB, minus the number of bonding divided by 2. So formal charge for hydrogen would be 1 minus 0 minus 2 divided by 2, which works out to be 1. 1 minus 1 is 0. Formal charge for nitrogen is its valence electrons is 5. It's in the group 5, minus 0 non-bonding. There's no lone pairs. So that's 0. And then you have 8 electrons divided by 2. So that would be 4. 5 minus 4 is 1. So the formal charge, and how you do this, you would put a plus in a little circle to show the formal charge for nitrogen is plus 1. Now, the other thing I want to note here is that I didn't check to make sure that everything has its complete octet or duet, and nitrogen does. And here nitrogen has 1, 2, 3, 4, 5, 6, 7, 8. 8 electrons. So it's complete. Okay, this is problem 9-6. Okay, once again, did I say 9-6? I meant 9-7. Okay, so this is 9-7. Once again, we're writing a Lewis structure for chloric acid, and we want to optimize formal charges. When it talks about optimizing formal charges, there is the formal charge rules, and those rules are on page 403. And basically those rules state that you sum all formal charges in a neutral molecule must equal to 0. So this molecule, unlike that last molecule where we had ammonium, these have to sum up to 0. The formal charges got to sum to 0 because it's a neutral molecule. The second rule says sum of all formal charges have to equal the charge on the ion. So the last one, where we did ammonium, the formal charges had to sum up to a +1, and it did, because remember the hydrogens were all 0 and the nitrogen was a +1. So that's your rule. Okay, the third rule, and this is where we talk about optimizing. Excuse me. Sum or 0 formal charges on individual atoms are better than larger ones. So if the sum is small, you want the small or a 0 formal charge on the individual atoms. The smaller they are, the better. They're better than large ones. And the fourth rule is when formal charges cannot be avoided, you want your the negative formal charges should reside on the most electronegative atom. Okay, so let's just go ahead and write our Lewis structure, and then we'll talk about formal charges for chloric acid. The first thing, you want to draw your skeletal structure. Remember, this is page 395. And so when you draw your skeletal structure here, hydrogen is going to be a terminal, and then you've got 1 chlorine and 3 oxygens. And typically they're written like this. I've said this before. If you wanted to look on page 395, you would see that chlorine has a 3.0 electronegativity, oxygen has a 3.5, hydrogen has a 2.1. You don't have to memorize this, as if you increase your electronegativity going up and over, you could see that oxygen is above chlorine, so it would have a higher electronegativity. And that would make your most electropositive element chlorine, and that would be the central position. The second thing you're going to do is you're going to total your total valence electrons for this molecule. So we have hydrogen is in group 1, and there's 1. Chlorine is in group 7, and there's 1. Oxygen is in group 6, and there's 3. There's no charge on this, so you don't have to worry about adding or subtracting electrons to that final account. So you have 18 plus 8 is a total of 26 valence electrons. Okay, the next thing you want to do is distribute these electrons, and so go ahead and count the bonds. 1, 2, 3, 4, 5, 6, 7, 8, and then you distribute the rest to the terminal positions. 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26. And there you go, 26 valence electrons. The next thing you do is you check to make sure hydrogen has a duet, 1, 2, it's satisfied, and the rest of the elements have a complete octet. So here, this oxygen has 1, 2, 3, 4, 5, 6, 7, 8. That one's fine. Check this oxygen. 1, 2, 3, 4, 5, 6, 7, 8. That one's fine. Check this oxygen. 1, 2, 3, 4, 5, 6, 7, 8. That one's fine. And then check your chlorine here. 1, 2, 3, 4, 5, 6, 7, 8. That one's fine. So that's how you know you've drawn a correct Lewis structure. Now you want to do formal charges for each element. So a formal charge for hydrogen, if you remember your formula, it would be 1 because it's in group 1, and you're going to subtract the number of non-bonding electrons is 0, and then you're going to add the number of bondings divided by 2. And so that gives you a 0 formal charge for hydrogen. Formal charge for chlorine would be 7 minus 0 plus 8 divided by 2. So what is that? That's 7 minus 4. So that is going to be a plus 3 for chlorine. Plus 3. You kind of write it in there like that. And then formal charge here for oxygen is 6. It's in group 6 minus how many lone pairs? And all these oxygens are equal because they're all bonded the same. They have 3 lone pairs and a single bond. So we only have to do this one time. If it was bonded differently, which you'll see, then you have to do it for each different type of bonded oxygen. But here we have 6 minus how many lone pairs? Electrons? 6 plus 2 divided by 2 because you have 2 bonding divided by 2. So this works out to be 6 minus 7 is a minus 1. So each one of these is minus 1, minus 1, minus 1. And so you got 3 plus and 3 minus. That's a neutral. Now, the key here, it says optimize. So this is not optimized. If you look at the rules on page 403, you might want to open that book up and look at that. The problem with this is it's okay that the negative, you got a negative 1, right? The negative 1 on the oxygens are on the most electronegative atom, 0, okay? Actually, chlorine is a plus 3. That's a large. That's the only thing that's concerning here is chlorine is a plus 3. Now, these could, chlorine could form a double bond to an oxygen. So let's see what that would look like. H, chlorine, double bond, oxygen, oxygen, oxygen. Now, if you did this, you still have 26 valence electrons. So you put those in 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26. And in that case, your formal charge, and you can work this out. Let's look. Of course, hydrogen stays the same, so it's going to be 0. Your formal charge for your chlorine would be 7 minus 0 plus, now you have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 10 divided by 2, which is 5, and 7 minus 2 is a plus 2. So that would make chlorine a plus 2. The oxygens are still bonded the same here, so these are minus 1. And this oxygen, I'm an organic chemist, so let me just tell you, I know that oxygen for a formal charge of 0 is going to have always a double bond and 2 lone pairs. So in that case, this one's 0, and you see plus 2 and minus 2. Now, you notice here that I expanded the octet here for chlorine. And when you expand why can I do that? Because look at that, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Now chlorine has 10 electrons. It doesn't have the octet of 8. Well, if you read in section, where's your exception? Exception to the octet rules. Expanded shells. That is on section 9.9, page 406. And basically any elements that are in N equals 3 or greater, because they can actually have a higher octet number. So in that case, you can optimize the formal charges a little bit more here. Would that really happen? Quite possibly, I'm not sure. But make sure that you read section 9.9 on page 406 so you understand about expanded octets. Which one's better? I don't know. Because I don't know what would be better, to expand the octet or have a higher formal charge. So you won't get something that gray area on your exam. Okay, let's go to the next problem. The next problem is problem 9-8. And once again, we're writing a Lewis structure for the product here. So the most common of these, phosphoryl chloride. And you want to draw the Lewis structure for phosphoryl chloride and optimize the formal charges. So let's see. Basically, phosphorus is going to be the central position, and you have 3 chlorine, and then you have oxygen. Now, phosphorus is, if you look at the periodic table, remember electronegativity goes up and over for increasing electronegativity. Phosphorus and chlorine are on the same row, and phosphorus is closer to the left-hand side, so it would be more electropositive chlorine, and these are also under oxygen, so phosphorus would be your most electropositive element, and that is why it's in the central position. Okay, so we've drawn our skeletal position, and now we are going to total our valence electrons. Now notice there's no charge here, so we don't have to worry about that. So we're just going to add them up. So chlorine, so we have 3 of them, and it's in group 7. So 3 times 7 is 21 valence electrons. Oxygen, there's 1 of them, and it's in group 6, so that's 6 valence electrons. And then phosphorus there's 1, and it's in group 5, 5 valence electrons. If you add that up, it gives you a total of 32 valence electrons. So let's go ahead and add those in. 1, 2, 3, 4, 5, 6, 7, 8. Now we're going to fill up everything on the outside. 8, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30, 31, 32. And we're going to check to make sure each element has a complete octet, and you will see that they all do. So this one has 8. If you count each one of these, each have 8. So that's a fine Lewis structure, and you're totally fine with that, and that's actually correct. Now, but it says it wants you to optimize formal charges. Well, when you optimize formal charges, you got to look at your formal charge rules on page 403. So you need to kind of memorize those. The first 2 are easy. Sum all formal charges in the neutral molecule must equal 0. Well, this is a neutral molecule, so we're fine with 1. Sum of all formal charges in an ion must equal the charge of the ion. Well, we don't have an ion here. The third one, the sum needs to be small. The smaller, the better. And then the fourth one, when formal charges cannot be avoided, your negative formal charges should be on your most electronegative atoms. So here, the only reason why you could consider making double bonds is because phosphorus is in group N equals 3. And N equals 3 or greater can do an expanded octet. So we can go ahead and you can go ahead and do your formal charges. Here for oxygen, you will find that oxygen has 6 valence electrons minus, in this case, 1, 2, 3, 4, 5, 6, 6 non-bonding electrons plus 2 divided by 2 bonding electrons. So this ends up being a negative 1. And so then you'd write a negative 1 by the oxygen. Formal charge for chlorine, 7 minus 6 non-bonding plus 2 over 2, and that would be 0. So each one of these are 0, and zeros you don't write anything. Formal charge for phosphorus, but you can just look at it and guess what it's going to be. You guess it's going to be a plus 1 because it's got a sum 0, right? Well, let's just check. Phosphorus it's in group 5, minus how many non-bonding? 0, plus 1, 2, 3, 4, 5, 6, 7, 8. 8 divided by 2 is 4, and 5, that's a plus 1. So it is a plus 1. And in that case, that would probably be better than if you did an expanded octet, but I'm just going to show you how you would do that if you did. You can make double bonds. So these two lone pair here would go into the oxygen-phosphorus bond, and then you would redraw it. And what would that look like? So you redraw that. You draw everything else the same. Welcome to problem 9-9. Okay, this is free radicals. So if you remember in free radicals, this is actually, I think it talks about these in section 9.9, page 406. And in that section it talks about the exceptions to the octet. And one of the exceptions octet is free radicals because they form an odd number of valence electrons. These molecules have an odd valence number of electrons. So if you remember correctly, for each of the molecules we've been drawing Lewis structures for, they each have an even number. So this is going to be the first time you see the odd. So let's just go ahead and start this. Nitrogen, you would just draw with 5 valence electrons. It's in group 5. And then nitrogen oxide, you would draw N-O. You don't have to worry about a central atom because you only have 2 elements here. How many valence electrons do we have? Well, nitrogen has 5 and oxygen has 6. So 5 plus 6 is a total of 11 valence electrons. And then you put them together. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Okay, well, as you can see, that's not going to fit the octet. So nitrogen does not have a complete octet, and neither does oxygen. So we're going to end up making double bonds. So let's go ahead and make a double bond here. And then you redraw this. I'm going to put the single lone electron on nitrogen. And I'll tell you why I'm going to do that here in a minute. Okay, so here we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. And we don't have a complete octet for oxygen here because 1, 2, 3, 4, 5, 6. So then we can draw this as such with nitrogen does a double bond to oxygen. And let's put 2 electrons here. So that completes this octet. And then 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. And nitrogen here has 1, 2, 3, 4, 5, 6, 7. It's not going to have a complete octet, so it's because it has an odd valence electron. But the good news is we did put it on nitrogen. Nitrogen typically forms free radicals, and it's the more electropositive element, so it would have the free radical. And then you want to draw the product, which is N oxygen. And basically here we have the 11 valence electrons from NO plus another 5 from nitrogen. So we have a total valence electrons of 16 valence electrons. We already have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. And as you can see, this nitrogen, the outer nitrogen has a complete octet. The outer oxygen does, but the central nitrogen only has 4 electrons. It has an incomplete octet, so we're going to have to make some double bonds. Oxygen really likes two lone pairs and 2 bonds, so we'll just go ahead and move those electrons there, and then we keep everything else the same. And when we check this out, we'll see that this nitrogen's fine and the oxygen's fine with its octet, but the central nitrogen only has 6 electrons and it needs 8. So we're going to form another double bond, and we'll move this nitrogen's double and make a nitrogen double bond. And when we redraw this and we put in the electrons, that should be a nitrogen. We put in the lone pairs that did not move, and we will see that now nitrogen has a complete octet, the central nitrogen does, and the oxygen does. This problem does not ask for formal charges, so we won't worry about it. You could calculate the formal charge if you wanted to. Just for kicks, you should get a formal charge for the oxygen of 0. This nitrogen would be 5 minus the central nitrogen. 5 minus 0 plus 8 divided by 2 is 4. So that would be a plus 1. And then this nitrogen would be a minus 1, which would sum up to 0. So that would be the correct Lewis structure. It's also kind of interesting if you look at this, what's happening is this nitrogen is combining, so it has an odd number of electrons, and it's combining with NO, which has an odd number of electrons. Let's draw with this NO to form this new NNO, which has an even number of electrons. Okay, this is problem 9-10, and this is a re-recording. So I've already have drawing on here, but I'm just going to go through it. So this is section 9.9. It's page 406, expanded octet. You need to read about expanded octet on page 408, example 9.0. So basically an expanded octet can happen because Xeon is in group 5, in row 5, n equals 5. Anything with n equals 3 or larger can form an expanded octet. So in this case, you do your Lewis structure for these 2 compounds here, Xeon with 2 fluorine, and you get a total of 22 valence electrons. you put the electrons around the terminal, and then you put the remaining electrons onto Xeon. So as you can see, fluorine here has 3 lone pairs and a single bond. It has a happy complete octet, and Xeon gets the extra electrons. Now, you can also form a double bond because, so in the Xeon F2 oxygen compound here, you do the same connectivity, except you're going to put oxygen now on Xeon, and to add up your total valence electrons, it's basically 22 because you have Xeon with 2 fluorine, plus now you have oxygen, so you add another 6, that's 28 valence electrons, and you add the valence electrons on the terminal elements, and then you see that every element has a complete octet, and Xeon has its 2 lone pairs. But I know that oxygen prefers a double bond with its 2 lone pairs. And when I say prefer, that means it gives a formal charge of 0. And so you can see the blue box, Xeon, with the 2 fluorine and the double bonded oxygen, is the best Lewis structure. This is problem 9-10. So it says draw a Lewis structure for SO2. Show all formal charges. So here we have sulfur in the middle, because if you look at your trend, increasing electronegativity goes up and over, and sulfur is under oxygen on the periodic table. So that would mean it's more electropositive and would have a central position. This is just writing Lewis structures. Now you want to total up your total valence electrons. So sulfur is in group 6, so it has 6. Oxygen is in group 6, so it has 6. And there's 2 of them. So 12 plus 6 is a total of 18 valence electrons. Now, just like we always have done, you add your valence electrons, and you count up 18 and you add them to the terminal. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. After you add up all your total valence electrons, you check to make sure each element has a complete octet. Oxygen does, this oxygen does, sulfur does not. It has only 6 electrons. It does not have 8, so therefore it doesn't have a complete octet. So we're going to have to redraw this. The way we want to do this is we're going to take these 2 electrons here and we're going to form a double bond. So the nice thing is we can just redraw this as a double bond to oxygen, and then all the other electrons stay the same. And you can count that up and you'll see that that's 18 valence electrons. Let's check our octet. Oxygen does, yes. Sulfur, 1, 2, 3, 4, 5, 6, 7, 8, it does. And this oxygen does. So this is a perfectly fine Lewis structure. However, we're going to show formal charges. And then it wants us to draw a Lewis structure that has a formal charge of 0, that all atoms have a 0. So let's figure out the formal charge. Formal charge of your first oxygen. Well, 6 minus, there's 6 non-bonding electrons, plus 2 divided by 2 bonding electrons. So that ends up being a minus 1. So oxygen has a minus 1, the first oxygen. Formal charge of your sulfur, 6 minus 2 non-bonding electrons plus 6 divided by 2 of bonding electrons equals 6 minus 5 is a plus 1. So this is a plus 1. And then this oxygen, if you do formal charge of the last oxygen, you'll see that it's 6 minus 4 non-bonding plus 4 divided by 2 bonding electrons, which equals 0. And we don't write that in when it has a 0. Plus minus and minus plus 1 and minus 1 total up to 0. It's a neutral molecule. It's a perfectly fine Lewis structure. However, we want the molecule to have all atoms to have a formal charge of 0. The way to do this is to make oxygen with 2 non-bonding lone pairs and 2 double bonds. So a double bond, so 2 bonds. So when you redraw this here, you can see you draw everything the same. Now the reason why, when you check this out, you'll see that oxygens follow the octet. Now sulfur has an expanded octet. And you're allowed to have expanded octets for any elements that are n equals 3 or larger, and sulfur is. So the formal charge for each one of these oxygens now, because they're bonded the same, they have 2 lone pairs and they have 2 bonds, which we call a double bond. That's going to be formal charge of 0. Formal charge for sulfur now, we have 6 minus 2 non-bonding electrons plus 8 divided by 2 bonding electrons. So this is 6 minus 6 is 0. So this is the correct structure for this problem. This is problem 9-12. Now I apologize, this is a re-recording, but I'll just go through it. So for the Born-Haber cycle, you need to read pages 386, 387, and 388. Listen to lecture 9.2. Here we're having just different delta H's of formation, delta H of sublimation, ionization energies 1 and 2, delta H of electron affinity, binding energies, and the question is asking you to determine the lattice energy of MX2. So the nice thing is you're given the formula here, and the formula says delta H of formation, and you basically add these together. So you just plug and chug in the formula. Negative 881 is from the enthalpy of formation. Ionization energy 1, well, that's given to you here, 793. Your delta H of sublimation is 139. And you just add all these together. 1,374 is your ionization energy 2. Looking above, you see the binding energy is 205. Your delta H of electron affinity is negative 339. And then what you're doing is you're solving for the delta H of the lattice energy. So then you plug and chug. So negative 881 equals 2,306 plus a negative 473. You solve for your delta H. Then you have negative 881 equals 1,833 plus the delta H. The delta H of lattice energy is negative 2,714 kilojoules per mole. And the reason why you can use this formula is because delta H is a state function, so it's independent of path. So we can sum up all the delta H's from the different processes to figure out one little piece of the puzzle, like the delta H of the lattice energy.